Hello, and welcome to our first lecture on exponential and logarithmic functions. In the next 5 lectures, we'll see many applications to compound interest, radioactive decay, and even probability and statistics. This is a rich area of mathematical applications. So exactly what is an exponential function? Well, we've seen polynomial functions like x squared, and we've seen like the square root function or the cube root function. The cube root function can be written as x to the 1/3 power. And in both of these functions, notice that the variable's down at the base and the exponent is a number. Well, exponential functions flip-flop that. Now the number is the base and the variable's hiding up there as an exponent. For instance, a common exponential function is f of x equals 2 to the x power, or f or g of x equals 1/3 all raised to the x power. These are typical examples of exponential functions. Let me give you the formal definition of an exponential function. The exponential function f with base a is denoted by f of x equals a to the x. And here a, the base, is greater than 0 and not equal to 1. And x is any real number. Now, why did I say a is not equal to 1? Well, if you have the base 1, then your exponential function would be 1 to the x power, which is just 1. And that's not a very interesting function. That's the horizontal line 1. So generally, we omit the base 1 with exponential functions. And we also omit negative bases. You got to be very careful when you take -2, say, to the x power. That expression is not defined over the real numbers for many values of x. For instance, -2 to the 1/2 power means the square root of -2, and we know that's not a real number. In fact, I invite you to graph the function -2 to the x on your graphing calculator. You'll see a strange picture appear. Good. Let's talk about some exponential functions. Perhaps the easiest example, the most basic, is the function 2 to the x power. Now, what do we mean by this? Well, you can plug in values for x. For instance, f of 3 would be 2 cubed, or 8. And f of 0 is 2 to the 0, or 1. And f of -2 would be 2 to the -2, which you remember means 1 over 2 squared, or 1/4. And now, what's the picture of 2 to the x? What's the graph going to look like? Well, one way to produce the graph by hand is to do a table of values. So for different x values, like -2, -1, 0, 1, and 2, you then compute f of x, you compute 2 to the x, and you get values like 1/4, 1/2, 1, 2, 4, and 8. You plug in those x values and compute 2 to the x. Then you connect those points with a smooth curve. And here's the graph. Good-looking graph, isn't it? A very interesting graph. Sort of keep this picture in mind as we progress through these next few lectures. This is a very typical picture of an exponential function. I've indicated some of the points that we just evaluated. One of the key ones is 0, 1. That's the intercept. When x is 0, y is 1. And another interesting feature of this graph is that there's a horizontal asymptote to the left. As x gets very negative, the function is getting closer and closer to 0. There's a horizontal asymptote to the left. Okay. I computed some function values 2 to the x, and I used some properties of exponents there. You might have noticed we did 2 to the -1 power, or 2 to the -2 power. Those properties of exponents that I just used kind of freely there are often complicated for students. And let me take a moment to review some of the properties of exponents. This might be a bit tedious if you're very familiar with exponents, but it's worthwhile to take some time reviewing these properties, I think. So let's assume that a and b are real numbers and m and n are integers. Here are some properties of exponents. A to the m times a to the n is a to the m plus n. You add the exponents. For instance, 3 squared, 3 to the 2 power, times 3 to the 4th power is 3 to the 2 plus 4, or 3 to the 6th, which turns out to be 729. A similar property for quotients. A to the m divided by a to the n is a to the m minus n. For instance, 2 to the 5th divided by 2 cubed would be 2 to the 5 minus 3, or 2 squared, which equals 4. Here's some more properties. A to the minus n means 1 over a to the n. For instance, 5 to the minus 2 means 1 over 5 squared, which is 1 over 25. A to the 0 equals 1. And that's true for all a not equal to 0. 0 to the 0 is not defined in mathematics. It's kind of a confusing number. But a to the 0, where a is anything but 0, that's always equal to 1. Another property that's kind of obvious, I think, the absolute value of a squared is the same as the absolute value of a all squared, which is the same as a squared without the absolute value signs at all. Okay, good. Here's some more. The product AB raised to the mth power is the same as a to the m times b to the m. For instance, another quick example, 3x to the 4th power can be rewritten as 3 to the 4th times x to the 4th, which is 81x to the 4th. A similar property for quotients. A over b all to the mth power is the same as a to the mth divided by b to the mth. For instance, x over 2 all raised to the 3rd power is x cubed over 2 cubed, which is x cubed over 8. And there's another property. A to the m raised to the nth power. It's kind of a tower of exponents, isn't it? A to the mth, and then you raise that to the nth power. That's defined to be a to the power m times n. For instance, 2 cubed all squared would be 2 to the 3 times 2, which is 2 to the 6th, or 64. You can check that by saying, what's 2 cubed? 2 cubed is 8. And what's 8 squared? 64. Got the same answer. Okay, that was good. Those properties are, a little bit, I won't say that they're the most exciting properties in the world, but we have to manipulate exponents a lot in algebra, so it's good to have them in front of us. And in our workbook, we'll have these properties summarized back in the appendix. Here's a curious phenomena with exponents, and I've been asked this many times with students, the so-called tower of exponents. What does it mean to write a to the b to the c? 3 exponents, well, a number and then an exponent, and then that number has an exponent. What does that mean? Well, it doesn't mean a to the b raised to the c power, because that means a to the b times c. When you see a, b, c in a tower, what they mean is a to the power b to the c. The parentheses are up at the top. Here's an example of that. 2 to the 2 to the 3. Wow, a tower of numbers, 2 to the 2 to the 3 means 2 to the power 2 cubed. 2 cubed is 8, so it's 2 to the 8th, or 256. Okay, that's just sort of a sidelight there, tower of exponents. And by the way, mathematicians have studied towers with 4, 5, 6, and more. They keep going up. Let's look at another exponential function. Let's look at 2 to the minus x, which is the same as 1/2 to the x power. How would you graph this? How would you get a handle of this function? Well, you do the same thing we did with 2 to the x. You construct a table of values. And you could say, let x be -3, -2, -1, 0, 1, 2, and then evaluate the function at those values. And then you could connect those points with a smooth curve. And here's what you get. Another really interesting graph. This is what's called a decaying exponential. As you start, it starts off pretty high, and then as you go off to the right, it approaches a horizontal asymptote, which is the x-axis. Notice that it still has the same y-intercept at 0, 1, but this time it's decaying, whereas the function 2 to the x was increasing as we went off to the right. Here's something even more subtle here that I'd like to point out now. Does this graph satisfy the horizontal line test? Do horizontal lines touch the graph at most once? Right, they do, don't they? And they also do for the graph of 2 to the x, which we saw earlier. What does that mean? That means that these exponential functions are one-to-one. They have inverses, and those inverses will be the logarithmic functions next lecture. But that's getting ahead of ourselves. Here are some facts about exponential functions we should keep in mind. The domain is the set of all real numbers. They're defined everywhere. But the range is positive real numbers. Those graphs were above the x-axis. And the intercept was at 0, 1. Okay. The x-axis is a horizontal asymptote. And we saw that in both pictures. And the curve is a good-looking curve. It's continuous. It doesn't have any breaks in it. And it's smooth. It doesn't have any sharp corners and things like that. And as I said earlier, it's one-to-one. It passed the horizontal line test, so it does have an inverse. All right, let's play with some exponential graphs. Let's kind of massage them a little bit and see some related graphs. What does 3 to the x minus 2 look like? What do you think that looks like? Well, 3 to the x looks kind of like 2 to the x. The base has been changed slightly. But that minus 2 means it's shifted downwards 2 units. So the intercept of 3 to the x was 0, 1. Now it's going to be 0 minus 1 because the intercept has moved down. And what about that horizontal asymptote? It used to be y equals 0. Now it drops down to y equals minus 2. Okay, time for an application. What are these good for? This is kind of a neat application, and we'll see radioactive applications involving radioactivity a number of times in this course. Here's a fairly simple model. Let's let Y represent the mass in grams of a radioactive substance, and we're going to use strontium-90, and that has a half-life of 29 years. And there's a model for how much strontium-90 you have after T years. And I'll give you the model. It's 10 times the base 1/2 to the power T over 29. Kind of an awkward model, but you'll see how it works in a minute. Let me ask some questions about this model. What's the initial mass according to this model? Well, let T be 0. That's the initial mass. How much do I have right now? And when T is 0, 1/2 to the 0 is 1, and 10 times 1 is 10. So that 10 in front of the model is the initial amount of strontium-90. How much do I have when T is 29? When time is 29? Well, you would plug 29 in for T, and watch what happens. You'll see now what half-life really means. You plug in 29, and your exponent is now 29 over 29, which equals 1. And so it's 10 times 1/2, which means 5. And that's what half-life's all about. You start off with 10 grams, and 29 years later, you have half the amount. You have 5 grams. How much do you have, say, after 80 years? You would just plug 80 into the model. It's 10 times 1/2 to the power 80 over 29. You can't figure that out by hand. You'll have to use a calculator, and you get approximately 1.48 grams. Here's a picture of that model. It's a decaying exponential. It starts off at 10 when time is 0, and at 5, you see I've marked the point when the amount is 5 when the time is 29, and then further along when the time is 80, it's decayed off to be a very small amount. Okay. There's a great problem here from a long time ago that I thought I'd take a moment to show you. It has really nothing to do with developing the exponential and logarithmic functions, but it's really a neat historical piece of mathematics. And here's what I'd like you to do. I'm going to compute some values of a tower of exponents. I'm going to compute 2 to the power 2 to the first. Then I'm going to compute 2 to the 2 squared, and then 2 to the 2 cubed, and each time I'm going to add 1 to the result. So here's what I mean. Let's compute 2 squared plus 1. 2 to the power 2 to the first, which means 2 squared plus 1, that's 5. Okay? Now I compute 2 to the power 2 squared. Well, that's 2 to the fourth, which is 4. 2 to the fourth is 16, excuse me, and 16 plus 1 is 17. So the first two numbers are 5 and 17, and those are prime numbers. Let's do another one. What's 2 to the power 2 cubed? Well, I need a calculator now, but that turns out to be 257. It's also a prime number. Let's do it for 4. 2 to the power 2 to the fourth plus 1. That turns out to be 65,537. It's a prime number. Well, back in the 1600s, Pierre de Fermat conjectured that this sequence of numbers that we're computing, one after the other, would always be prime numbers. He thought they would always be primes. And the first four are 5, 17, 257, 65,537. Well, what's the next one? Well, you need a calculator for this, and poor Pierre de Fermat didn't have calculators back there, but it turns out to be 4,294,967,297. Whoa, big number. Fermat thought that was a prime. And he's wrong. It's not a prime number. It can be factored into two smaller numbers. He never discovered that. His conjecture was wrong. That number can be factored into two primes, but he was never able to do it. The primes are 641, that's not too big, and the other prime is, watch out, here we go, 6,700,417. Trust me on those computations. So it's a great historical note that even the greatest mathematicians can make mistakes. Okay, we turn now to the exponential function again, but now we're going to use a new base. We've talked about the base being 2 to the x, or 3 to the x, or 1/2 to the x. Well, it turns out that the most important base is a number called e. Okay, don't panic now. E is a strange number. It's in between 2 and 3. It's about 2.71828. E will occur repeatedly in this course as we develop ideas of logarithms, exponents, trigonometry, etc. E is such an important number, it's built into calculators. The manufacturers of calculators know that they have to put this number inside the calculator and have it available, much like the number pi is such an important number in mathematics and applied mathematics. This number dates back to Napier in the 1500s, and when he was working on the development of logarithms. The letter E was chosen by the Swiss mathematician Euler, one of the greatest mathematicians of all time, in 1727. The story is that he chose E because it's the first letter of exponential, and not because it's the first letter of his last name. Let me try to motivate E a little bit. This is hard to do. The first time you see E, you sort of go, why do I care about this number? What's it for? I don't understand it. I don't like it. I like 2 better. I like 3 better. But E is more important, it turns out, than any of those other numbers. Let me try to motivate it. I'm going to look at an expression that's kind of weird looking. It's 1 plus 1 over x, that quantity raised to the x power. All right, it's kind of a funny looking expression, isn't it? 1 plus 1 over x, all raised to the x power. And I'm going to plug in large values of x, and some magic will occur here. So I'm going to make a table of values. X is going to be, say, 10, or 100, or 1,000, or 10,000, or really big, 100,000. And then I plug it into this expression. And you can do this at home with your calculator. You can plug in x for these numbers and see what you get. Well, when I plugged in 10, I got 2.5937 approximately. Then I plugged in 100 and got another number. And say at 100,000, I got 2.7183. You recognize what's happening? What's going on here? Well, as x gets bigger and bigger, this funny expression is getting closer and closer to that magic new number called e. In fact, in many textbooks, the definition of e is the limit as x goes to infinity of this expression, meaning you take higher and higher numbers, bigger and bigger numbers, it gets closer and closer to that value of e. In calculus notation, in case you take a calculus course, you would write it as follows. The limit of that expression, the limit of y, where y is equal to that expression, as x approaches infinity, as x gets larger and larger, equals e. Great. So, for the moment, just accept that e is going to be the base of our exponential function. Think of e as being between 2 and 3. It's a little bit closer to 3, isn't it? Here's the graph of f of x equals e to the x. This is the natural exponential function. It's built into your calculator. E to the x is a built-in key on your calculator. All right, we now have the natural exponential function. E is the base of that natural exponential function. Let's do an application. And I'm going to go back to compound interest now, which we talked about a little bit in lecture 1. But I'm going to complicate things slightly. Back in lecture 1, we had a certain amount of money that we deposited, and we compounded annually. Well, suppose you compound quarterly, or you compound monthly, or you compound daily. Well, the formula changes. And here's what the formula looks like if you compound n times per year. The amount of money you'll have in your bank is A, the amount in the bank, equals P, that's the amount you deposit at the beginning, times the following expression, 1 plus r over n, all raised to the nt power. Now, who are these characters? P's the amount you deposit. A's the amount you have after t years. So t is up in that exponent. And n is the number of compoundings per year. N might be 4 if you're compounding quarterly. And r is the interest rate. And you write that in decimal form. So if it's 5% interest, you would write it as 0.05. Good. So that's a nice formula, and it's easy to use. In fact, I'll use it in an example in a few minutes. But now think about this. Suppose you compound daily. Or suppose you have a bank that compounds hourly. Or you compound every minute. You compound every second. You compound every nanosecond. You compound all the time. And we call that continuous compounding. And this formula then takes on a new form if you have continuous compound interest. And it's the amount you have in the bank is equal to PE to the RT, where E is that new number we've been talking about. Wow. That's actually a simpler formula, isn't it? Continuous compound interest is pretty easy to work with. Let's do an example to show how these formulas work. Suppose you got $12,000 and you're going to deposit it in a bank at 3% interest. Let's find the balance after 4 years in 2 different cases. First of all, it's compounded quarterly, and second of all, it's compounded continuously. You think you'll have more money if it's compounded continuously? You would think so, wouldn't you? It's being compounded more often. You think you might have an infinite amount of money? Now, it's too bad you don't, but you have slightly more. Let's do the arithmetic. How much do you have? Well, it's p times 1 plus r over n to the nt power. Who are the characters? P is 12,000. N is the number of compounding, so n is 4. R is the interest rate, 0.03, and the exponent is 4 times 4. N is 4, and t is also 4 years. And if you punch that on your calculator, you get about $13,523.91. So you earn some money in those 4 years. How about continuous compound interest? Well, this is easier. It's 12,000 times e to the RT. R is 0.03 and t is 4. Punch that in your calculator, you get 13,529.96. As I said earlier, this function is in the calculator, so it's not like it's some obscure calculation. And notice your answer, you got a little bit more money, didn't you? What is it, about almost $6 more. Wow, made a lot more money by having continuous compound interest. Okay, let's play you be the teacher again. Kind of like to play this game as we go along. A student comes to you and says, Professor, I've been hearing that exponential functions are always growing. They talk about exponential growth. Is it true that all exponential functions are increasing? Are they all getting larger as I go out to the right? Is that correct? Is the student right to say that all exponential functions are increasing? Well, no. In fact, we've seen an example of an exponential function that's decreasing, haven't we? 1/2 to the x power, or 2 to the minus x, is a decreasing exponential. In fact, in applications, you'll often hear the following terms. You'll hear exponential growth, like that might model some bacteria growing, or you'll hear about exponential decay, like radioactive decay. So the exponential function can be an increasing function or a decreasing function. All right, here's a really interesting puzzle, and I want you to try this one with your graphing calculator. Let's look at two functions. One is 2 to the x, which is a function we've talked about today. And the other function is a polynomial, one of our old friends, x to the 10th power. Okay? 2 to the x and x to the 10th. Let me graph them for you real quickly. Here is a graph of x to the 10th, it's in green, and 2 to the x, it's in yellow. And I've graphed it on the interval from 0 to about 10 or 11. And I think you see that the green curve is on top of the yellow curve. In other words, x to the 10th seems to be bigger than 2 to the x. So here's my question. As x gets larger and larger and larger, which function ultimately will grow faster? Which function is on top after a long time? It looks like the polynomial is bigger for a long time, doesn't it? The polynomial looks bigger. It's on top. Is that true forever? Well, go to your calculator tonight and plug in a number bigger than 59. Whoa. It turns out that past 59, 2 to the x is bigger than x to the 10th. And this has an important engineering and application, or computer science application. Exponential functions, when they're increasing, increase faster than polynomial functions. Polynomial functions, sure, x to the 10th is pretty big, but that exponential function is even bigger. It just takes a while to show up. X has to be bigger than 59. That's a big number. Okay, now we've talked about this number e. Let me whet your appetite a little bit about the number e. Let me show you or tell you a little bit more about e. Again, the first time you see it, it's kind of like, whoa, where did that come from? What do we need that for? But e appears all over mathematics. It plays a major role in calculus, a major role in applications. First of all, e is an irrational number. It's not a fraction. It's not a rational number, which means a fraction. So it's much like the number pi. Pi is also an irrational number. You cannot express pi or e as a fraction. And E also has a representation as an infinite sum, whatever that means. What does it mean to add up an infinite number of numbers? But if you start adding up the following numbers, 1 plus 1 plus 1 over 2 plus 1 over what we call 3 factorial, which means 3 times 2, that's 1 over 6, plus 1 over 4 factorial, which means 1 over 4 times 3 times 2. You keep adding those up, you will get closer and closer to E. That's called an infinite series, and we'll talk about infinite series near the end of this course. But here's an expression for E that's just sort of out of nowhere. But again, if you take a calculus class, this kind of infinite representation of E is very, very important. Okay, I hope you've enjoyed this first exposure to exponential functions. The key point here is that they're one-to-one, and hence next lecture we'll be able to invert them. And the inverse is going to be our friend, the logarithmic function. So, see you next time when we talk about logarithms.